Hi, welcome to chemistry, and let's talk about matter. So matter is anything that has mass and takes up space. Let's talk about takes up space. I want you to think about what that means. We have some vocabulary for that, and you're going to be asked a question about that. And then as far as mass, that's one way that we can describe the amount of matter that we have. So in the metric system that we use in class, the gram is the standard unit of measurement. You've used that before in biology, I know, and maybe in middle school classes or in physics. And then I want you to think about some of those prefixes that we've used in the past. I know you're familiar with milli, which is 1,000th. So it takes 1,000 milligrams in order to make a gram. And then kilo, which is 1,000. So there would be 1,000 grams in a kilogram. Okay, and to help put that in perspective, like a mosquito, his mass or her mass might be around 2 milligrams. If you have a paper clip, the mass of a paper clip is around a gram. And if you have a really heavy textbook, the mass of that might be around a kilogram. And the instrument that we use to measure mass is called a balance. I know that you've used digital balances before in biology. I happen to have one at home. Let's see how that shows. Okay, so mine's not nearly as fancy as what we use in the lab, but you would be able to read off the number of grams here after you put whatever you want to measure the mass of on here. Okay, but it is a balance that we use in order to measure mass. All right. And I want you to think about something. Let's think about weight. Okay, let's talk about that first. So a scale, now there's a difference between a scale and a balance. A scale is what you use to measure weight. So at home, if you go and step on the scale to see how many pounds you weigh, that's measuring your weight, and that's different from your mass. Weight is going to incorporate the force of gravity acting on that mass. Okay, so whenever we step on the scale and it says that we're so many pounds, that's not in the metric system. So in the metric system, we're going to use newtons in order to talk about weight, and newtons would be kilogram meters per second squared. And the way you figure the weight of something is you take the gravitational acceleration, which here on Earth is 9.8 meters per second squared, and you multiply it by the mass. So let's say that we have a 1 kilogram mass. You multiply those two numbers and you would come up with a weight of 9.8 newtons. All right, so let's think about if we were on the moon. The moon does not have the same gravitational acceleration as we do here on Earth. Okay, there gravity has a lot less pull. So g, which is the gravitational acceleration on the moon, is 1.6 meters per second squared. So I want you to think about what would the weight of a 1 kilogram mass on the moon be? You're going to answer that for me. And then while we're on the subject of weight and mass and matter, the air around us, do you think that's matter? Think about the fact, does it have mass? Does it have weight? If we talk about air pressure or atmospheric pressure, you might hear on the news talking about we have a high pressure system or a low pressure system. When they're talking about that air pressure, that's really the weight of all of the air above you pushing down on you. So I want you to answer whether or not you think air is matter and whether it has mass. All right, let's make some observations about matter. There are different types of observations that we can make depending on the scale, like large scale, looking, big picture looking, versus smaller scale, kind of on a microscopic scale. So I'm going to do a little experiment with baking soda and vinegar. All right, we can learn a lot of stuff with baking soda and vinegar, and it's also very safe. Okay, so I have baking soda in the container. I have a little vinegar here. What do you think is going to happen? And there it's fizzing. I think you can see that. All right, so what I see right now, that's an observation with my eyes or with all of my senses. I can smell the vinegar, I could hear the sizzle. Those types of observations are what we call macroscopic observations. Okay, those are big picture. Macro means large. Those kinds of observations don't require a microscope. It's what we see. All right, then we can go on to what we call microscopic observations. Okay, there you're looking with the microscope. Now, if we were to look under the microscope at the vinegar and baking soda solution, whenever I mixed it together and it had a reaction, if we were to look at that under the microscope, it wouldn't look a whole lot more different than looking at water. So atoms, you can't see those with a microscope. Those are way too small. You have to have a scanning electron microscope in order to see on the atomic level. Okay, the compound light microscopes that we use in class, there is no way that they would be able to see what's happening on the atomic level. Again, if you were to look at this under the microscope in class, we would just see what looks like water. Okay, so atoms are so small that they can't be seen with a microscope, excuse me. So we call those submicroscopic. That subroot means under. So it is smaller than the microscopic level. Okay, and then the structure of matter, the composition of the matter, what it's made of, and how it behaves, how those individual atoms interact. Those are all explained on that submicroscopic level or the atomic level. So I have here an example. Acetic acid, that's another name for vinegar. Vinegar is just very weak acetic acid. If I mix vinegar and sodium bicarbonate, which is baking soda, then I'm going to make a new product. There's sodium acetate, which is dissolved in water, and then that fizzing that we saw, that's carbon dioxide bubbling off. Okay, so that explains on the atomic level what happened in that reaction. Okay, and then we can go even smaller than the atomic level. We can go on the subatomic level. That means what's inside the atom. And I know that in physical science, you learned about the fact that there are protons, neutrons, electrons that make up the atom. And we will certainly learn that in more detail in chemistry. But that's what we mean by the subatomic level, is those parts that make up the atom. Okay, and then a little bit more about observations about matter. Chemists use many different types of models in order to explain what goes on with matter. So we've already looked at some different types of models. A macroscopic model, what can you see? We can do a particle model. So there's a particle model here that shows the difference in the spacing between particles and the amount of energy that you may have, the amount of kinetic energy seen in the various states of matter. So like a solid, a liquid, a gas, or plasma. Those are some particle models. So it's showing a particle of whatever we're talking about. That could be an atom if we were talking about an element. It could be a molecule if we were talking about a compound. But that's one example of a model. Atomic model, that's what I've already shown you whenever we looked at that baking soda and vinegar reaction. Subatomic, what would be going on with those electrons in order to make the bonds in order to make a new product. Lewis structures, that's a type of model that we'll be using this year, where we can draw representations of the bonds that exist between individual atoms in order to explain how a molecule is put together. And then there's some mathematical models that we'll look at. Okay, and then to finish up, our last slide, we're going to talk about the states of matter. Just a review from what you've already learned in physical science. We have solid, liquid, and gas, and then there's a fourth state that we learn about called plasma. Okay, so what makes a state? What defines the state? For one, it's the energy of the atoms in that piece of matter that we're looking at. So how much kinetic energy do they have? If we're talking about a solid, they have very little kinetic energy. Solids, the particles in a solid are vibrating very, very slowly, wouldn't be perceptible, but there's a little bit of motion there. Okay, if we move on up into the liquid state, those particles are vibrating faster and they're slipping past each other. Okay, if we move into the gas phase, those particles are bouncing around very quickly. There's lots of kinetic energy there. And then you can move into plasma, which is kind of similar to a gas. It's a very high energy state, and it's where the atoms of that gas, the electrons have been stripped off. So we really have ions and electrons that are moving around. That's the highest energy state for plasma. That's what we would see like in the sun, or maybe even lightning is an example of plasma. Okay, and then also in describing about the physical location of where those particles or atoms are in that state of matter. If we're talking about solids, those particles are packed in very closely, very densely. In liquids, they're spaced out a little bit and they can slip past each other. And then if we're talking about gases, they're spaced out even further and they're bouncing around randomly, occasionally colliding, but there's a lot of space between atoms. And then with plasmas, same thing, is those atoms, or actually they're ions now because they've had the outer electrons stripped off and it's a nucleus, it's a charged nucleus. Those ions are spaced out very far from each other and still bouncing on and making collisions. But there's a lot of space between individual ions. All right, so that wraps it up for your introduction to matter. Make sure that you've taken care of your Ed puzzle, and I will see you in class. Bye.